But let me say something else which outside the laws of known physics. And this is not something that people normally even recognize as a problem. I mean, they do, but they shove it under the carpet, which is what's known as the collapse of the wave function.
Mm-hmm. Mm-hmm.
Now, you see, current quantum mechanics, strictly speaking, is an inconsistent theory. That's rather a brutal way of saying what Einstein and Schrödinger and even Dirac said, that quantum mechanics is incomplete. And the way to explain this is, okay, there's a wonderful equation which tells you how a state evolves in quantum mechanics called the Schrödinger equation. Now, the Schrödinger equation tells you, if you know what the state of a system is now, the Schrödinger equation tells you what it will be tomorrow, if you like. The evolution of that state is governed by this wonderful equation due to Erwin Schrödinger. The trouble is that it doesn't. That's to say, the way physicists usually use the Schrödinger equation is to work out certain probabilities of what an observation on the system would tell you. So what you have to do is you wheel out of the cupboard a measuring device. In this measuring device, you set it on the system, which is evolving according to the Schrödinger equation, and it measures it. And the process of measurement does not follow the Schrödinger equation.
Right.
It gives you a probabilistic answer, this or this or this.
So that's another outside the system problem.
Well, it's certainly outside the Schrödinger equation.
Right.
And Schrödinger was terribly worried about this. I mean, he produced his cat in a box and all sorts of things. You see, he clearly realized there was a problem, as did Einstein. There's no question about that. Some others didn't. Well, they took a different view. They said, look, we don't understand the theory well enough. And that's more that we're saying. Where Schrödinger was not saying that. He was saying we understand it well enough to see that that's not the way the world operates. When you make a measurement on a system, it does not follow the Schrödinger equation. And that's what people understand about quantum mechanics. But it's a sort of vague set of rules about, it doesn't tell you what constitutes a measurement.
Right.
That's the trouble.
Right. Yeah, that's a big trouble.
That's the big trouble.
Yeah.
They say if you do a measurement, then it just becomes probability for what this or that or the other. But it doesn't say what kind of a device makes a measurement. Now, there's one school of thought, which has been going on from way back to the early days of quantum mechanics. Wigner, in particular, promoted this point of view, that it's a conscious being observing the system, and that makes
That's what
the
Wheeler
measurement.
believed, I believe.
I think Wheeler might have believed. Quite a lot of people believe that. I think von Neumann had a similar sort of view. I'm not quite so sure about his view, but certainly Wigner. And I talked to Wigner about these things. Yeah. I got the feeling from Wigner he wasn't quite as dogmatic he was made out to be on this issue. He just thought this was a possibility, I think. But anyway, people often refer to it as the Wigner view, that it's a conscious being who makes the measurement. That's not my view. My view is that it's almost the opposite of that view, that there is an objective physical process which deviates from the Schrödinger equation, in which the state does collapse so that it becomes one or the other with certain probabilities. And that this has to do with when gravity is brought into the picture. And there's reasons for believing this. I don't want to go into that. But there is reason.
I'd like you to go into it if you would be willing to, because I'm very.
Well, it's a very clear mathematical calculation. There's not a question about it. It's a question of what you do with it, you see. And what you do with it, according to me, is to say, okay, it tells you that this system has a lifetime, and it will, in that lifetime, become one or the other.
Without a measurement.
It's sort of, that's right, yes. Without a...
Well, it's so interesting to me
right.
that you're interested in consciousness, and you see that consciousness in this Gödel theorem sort of manner. And I would think the most predictable thing for you to believe as a consequence of that would be that it is conscious measurement that collapses the quantum indeterminacy, the waveform. And yet you don't. You think that that statistical vagueness will collapse into something that's essentially, is it either or? Is it binary?
Well,
is it 0-1, the collapse?
No, you mean no, there's a probability it'll do one
right,
or the other. Yeah,
right. But when the probability collapses, I mean...
Well, if it's a two-state system, you see, you might have an object which is in a superposition of here and here.
Yeah.
It was Dirac's first lecture. I remember hearing that. And he took out his piece of chalk and said, well, and he was talking about atoms, you see. According to quantum mechanics, or a particle, so quantum particle can be here, or it can be here, or it can be in a state which is partly here and partly here at the same time.
Right.
And then he took out a piece of chalk, and people tell me he used to break it in two. I can't quite remember, because my mind was drifting away from what he was saying, and I was looking out of the window and thinking about something completely different. And unfortunately, it only came back after he'd gone on to the next topic. So I missed the explanation, which was probably a good thing, as I think back on it, because probably the explanation was something sort of to calm you down and stop worrying about the problem. I suspect it was something like that.
So you don't think that a conscious observer per se is necessary to collapse the waveform?
Absolutely. That is what I don't, I mean, I'm agreeing with you.
Yeah.
I don't believe that, yes.
But you do think that, if I'm not mistaken, that the presence of an observer in the universe, that is to say, that, or the observation of the universe by us, is that true to say, is fundamental to the universe?
Not really. That's an interesting question, but it's not part of my view. The world would be there quite independently of whether there were creatures of consciousness.
Yes.
Quantum mechanics has a fairly antagonistic relationship with general relativity. You see, in Einstein's general relativity, he envisions that space is curved, but it's nice and gently curved. You know, imagine a bowling ball on a mattress, a nice gentle curve. Quantum mechanics, because of something called the uncertainty principle, tells us that things can't be nice and gentle when you go down into the microscopic realm. In the microscopic realm, things are fundamentally uncertain, which means that they fluctuate. There's chaos. There is tumultuous behavior happening in the microscopic realm. And it's this jittery, tumultuous behavior in the micro realm that conflicts with the nice, gentle behavior of Einstein's theory in the macro realm. So the laws of the small, quantum physics, the laws of the big, general relativity, really smash into one another. They don't come together in any harmonious manner in the conventional way of looking at things.